Good evening, ladies and gentlemen. Thank you for joining us today. We are Team 5, and this is our pick and place robot. I'm gathered here today with Masden, Brandon, myself, Aaron, Alex, Harrison, Jonathan, Daniel, and Peter. And we will be presenting our pick and place robot as Team 5. I will first be discussing the project overview for the pick and place robot. Pick and place robot must be able to pick up 4 steel spheres, a minimum of 13 centimeters, move them from a start location into a drop location. They must be autonomously and manually controlled and use an Arduino MEGR and Arduino IDE. Here we have the overview for the pick and place assembly. We have them labeled in sections 1, 2, and 3 for the base plate, as well as rotary axis 1, rotary axis 2, rotary axis 3, and the gripper. Next, we have a side view of the pick and place assembly. As you can see here, you can see the gears in the gripper and the gears in rotary axis 1, as well as the servo motor attached to rotary axis 2, and the stands on the base plate. And finally, we have the top view of the pick and place robot, figure 1.3. I will now be passing it on to my colleague Harrison to talk about the base plate.
Okay, well thank you, Brandon. My name is Harrison and I'm going to be talking about the base plate. So in this figure you can see that the base plate has 3 main sections, S1, S2, and S3. And in the bottom right hand corner of the figure you can see that the base plate has leveling feet, and these adjustable leveling feet are used to make sure that the base plate is always normal to the surface and that it's not uneven and the robot is not operating on a surface that might cause it to tip over. The base plate has a section S3 of 13 centimeters higher than section S1 and S2. Section S1 and S3 are the same width of 12 centimeters with a 13 centimeter width for section S2. In this figure you can see that the base plate from the front side is 28.5 centimeters long. And this important figure shows the sizing of the through holes. The holes that will be holding the steel spheres in the location that they are before they're dropped off has a 6.5 millimeter through hole and an 18 millimeter through hole for the drop-off location holes. For our component list, it's important to note that we are using a Garolite G10 FR4 sheet for all 3 sections, section S1, S2, and S3. The 6061 aluminum square rods are going to be used for the legs that hold up section S3 elevated from section S1 and S2. And the leveling feet are size M6 with a 25 millimeter long thread. With crosshead screws, we have 8 of those of size M3. So for our design, we wanted to consider mathematical and design constraints, and we're going to talk about the applied stress, the plate deflection, our factor of safety in the failure modes, the material strength, dimensional or geometry constraints, our material cost, the manufacturability of this material, and the availability of this material. So the base plate sections S1, S2, and S3 are going to be made out of Garolite G10 FR4. This material has a yield stress of 310 megapascals, a Young's modulus of 16.5 gigapascals. It's easy to machine and it can also be purchased online and shipped for our manufacturing and assembly, and this makes it extremely convenient for our final production. For the loading conditions, this base plate has a total load of 1.42 kilograms, and this includes the total robot arm mass, the steel sphere mass, and the Arduino MEGR and the electrical components that will be associated with it. So after learning about the loading conditions for the base plate, we were able to create shear moment diagrams for each section, section S1, S2, and S3. And on this slide, I have presented section S1 shear with a maximum shear of 1.5 newtons. And it's important to note that our diagram shows a simply supported beam with a distributed load of Q1, which just simply represents the distributed load of the dead weight of the material that we'll be using. And we support reactions section S1A and S1B. For the section S1 moment diagram, you can note that the maximum moment is 4.5 Newton centimeters. For section S2, this free body diagram looks slightly different because the applied load of the pick and place robot arm is directly on section S2, and it also has an applied moment because of the robot arm that extends out across section S1. So we also took that into consideration in our design, and this led us to calculate a max shear of 17.1 newtons, and it's also important to note that this is also modeled as a simply supported beam. For the maximum moment of section S2, it is recorded to be 106 Newton centimeters, and we've calculated this and we use this calculation later for our maximum bending stress. Section S3 has the exact same maximum shear of 1.5 newtons, and it's important to consider here that these section S1 and S3 have the same loading conditions, so therefore the maximum shear and maximum moment are identical. And maximum moment, as I previously stated, is the exact same as section S1 for section S3 with a maximum moment of 4.5 newton centimeters. So for the bending stress of the base plate, we have a applied bending stress of 2.2 megapascals with a applied maximum moment of 106 newton centimeters as previously mentioned from section S2. So for our allowable stress calculation, we use the equation yield stress over N, where N is a factor of safety. And our yield strength of Garolite G10 FR4 is 310 megapascals, and we have a factor of safety of 2. And that yields the allowable stress of 155 megapascals. So it's important to note that the applied stress of 2.2 megapascals is much lower than the allowable stress of 155 megapascals. And this helps confirm that we can use the material that we selected and we can move forward with the rest of our calculations for the remainder of the pick and place robot arm. For deflection of section S1, it has a maximum deflection of negative 3.6 times 10 to the negative 4. Okay, so for the deflection of section S2, it has a maximum deflection of negative 4.3 times 10 to the negative 3 centimeters. This is a very small deflection, but it is a little bit more than section S1. For section S3, we have a maximum deflection of negative 3.6 times 10 to the negative 4, and it's important to note that this deflection is the exact same as section S1, and this is also a very small deflection value.
All right, thank you, Harrison. My name is Daniel, and I'll be presenting Rotary Axis 1 to you today. So here's a general overview of the entire robot with a focus on Rotary Axis 1. So the requirements of Rotary Axis 1 are to rotate the entire assembly around the base plate using a stepper motor, and also to provide a stable mounting platform for the entire rest of the robot assembly. Here you can see an exploded view of RA1. There are a lot of parts here, but do note that there is a 2-to-1 gear ratio, and you can see that here, as well as these various ball bearings to reduce friction, as well as different types of fastening hardware used in this application. So here's an overview picture of Rotary Axis 1, and as I mentioned, there is a 2-to-1 gear ratio, and essentially that's going to allow for more torque and also more accuracy, but with the cost of speed. And I've also added this bracket for structural rigidity, and essentially this is going to take any extraneous torque off of the gear train itself. So basically it's just going to allow the robot to function a lot more smoothly. And here you can see in blue is a limit switch or a micro switch, and this is an alternative to a rotary encoder so that we can home the stepper motor. So here's an isometric view of Rotary Axis 1 without the bracket, so you get a better idea of what's going on. And then you can also see the motor placement, which is underneath the base plate. So this was a major design consideration. There were a few options that I had. I ended up going with the bottom mount just due to simplicity. Really, any other orientation would just add too much complication, and this just works out very well. This micro switch actuator you can see in the top picture, and that is in white. And that's essentially just a collar with a long set screw, and when that shaft rotates, it will contact the micro switch and home Rotary Axis 1. And this placement of the micro switch actually allows for almost 360 degrees of motion, which is ideal. So essentially, no matter what orientation we put this in, the micro switch can just stay right where it is, and it'll give us the freedom to rotate wherever we want. Here's a side view without the bracket. And this gives you a better idea of the micro switch actuator, which I mentioned is in white. And essentially that collar will just contact the micro switch when the shaft rotates, and it can be adjusted if necessary. All right, so the first calculation I did for Rotary Axis 1 is the resolution calculation. And essentially the way I decided to do this is if we take the sphere's radius and we divide it by 2, so we have half the radius of the sphere. That is how much accuracy we want to have, because essentially if you think about a sphere going into a hole, if it's within half of the radius, it's going to end up falling into that hole. So that is where I base these accuracy calculations off of. And as you can see in the bottom, greater than 50% accuracy is required to get the sphere in the hole, and with a 0.9 degree resolution, which is a result of a 1.8 degree resolution at the stepper motor with a 2-to-1 gear ratio, we end up with more than enough accuracy with either step choice to get the ball into the hole. The next calculation is the actual load torque. So this incorporates the mass and the length of the entire robotic assembly that's attached to RA1. And you can see all those variables on the right-hand side. We ended up with a load torque of 0.0066 Newton meters. And that's also assuming a speed of pi over 4 radians per second, which results in an acceleration of pi over 2 radians per second squared. And as you can see in this slide, the load torque comes into play here as well. This is our motor torque, or the required torque at the motor, as seen through the gear set. So that ends up being 0.0396 Newton meters, and then if we add a safety factor of 2 into the equation, we end up with a required torque of 0.0791 Newton meters. And for reference, the stepper motor that I've used in this in these calculations and in this project as a whole is rated at 0.16 Newton meters for the holding torque. So this will be, that'll be more than enough torque to drive rotary axis 1. So here you have a very simple stress calculation. This is just the stress that the rest of the assembly will apply to rotary axis 1, or specifically the bracket of rotary axis 1. And we end up with a stress of 234.78 pascals, which is very small. Just to further demonstrate that the bracket will be more than substantial to support the rest of the robot. Next up, we have our deflection calculation for the bracket. And to calculate this, I basically treated the bracket as a simple beam with a 1/8 inch material thickness and 5.95 by 4.35 inch dimensions. I also used 6061 aluminum with a Young's modulus of 68 gigapascals. And you can see the bracket diagram on the right just to help better illustrate this. And so here's the actual calculation. We ended up with 1/1000th of an inch deflection, which is very, very small, once again demonstrating that the bracket will be more than substantial to support the rest of the robot. So finally, we have our rotary axis 1 component list, and this essentially just highlights the mass and the quantity of each component of rotary axis 1. And here on the right, you can actually see the stepper motor that I have modeled in CAD and used for these calculations, as well as the micro switch that I've modeled in CAD and used for this as well. The most notable part of this slide would be the total mass, which is in the bottom right corner, and that's 0.812 kilograms. So pretty hefty, but the base plate will have absolutely no problem supporting this.
I will now be discussing rotary axis 2, the first arm connected, as labeled here in the diagram below. The main purpose of rotary axis 2 is to set the approximate height in order to set up for the gripper to achieve optimal ball retrieving. It needs to be able to move a minimum of 90 degrees. The design for rotary axis 2 uses a standard revolute joint with the servo motor directly connected to the pin using a keyway and key stock. It uses ABS plastic, and the torque analysis will be shown next. Here we have the CAD modeling for rotary axis 2. The servo motor connected to the servo motor's frame that is connected to the pin for rotary axis 2 in the bottom. And up top we have the gearing system for the connection of rotary axis 3, but it has to be mounted onto the outside of rotary axis 2. So here's figure 3.1, rotary axis 2. Here's the exploded view for rotary axis 2. As you can see, the parts here, we have an arm, 2 pins, some gears, the motors and the motor connection, the motor frame, and the base plate. This is figure 3.3, rotary axis 2 exploded view. Here are the beginning calculations for rotary axis 2, given the arm's mass, length, and target acceleration, and the mass of arm 2, because rotary axis 2 has to move the whole arm and everything attached, i.e. rotary axis 3 and the gripper. Our T total is going to be 0.135 Newton meters after a safety factor of 2 is applied to that, and the gravitational load. For the speed calculations, we have a target distance of 19.5 centimeters, and we achieve that for 12.41 radians per second. Here's the completed stress calculation to make sure no fractures occur within the rotary axis 2. We have an allowed stress of 14.8 megapascals, given our yield strength of ABS plinted plastic and our safety factor of 2. Here are deflection calculations for rotary axis 2. As you can see on the right, we have our free body diagram used to complete these calculations. Here we have the servo motor selection for rotary axis 2. The dimensions are given below with a maximum torque of 2.5 kilograms centimeters, way above our 0.135 Newton meter requirement. and it only takes about 4.8 volts to get there with a small weight of 14.7 grams. Here are the resolution calculations for Rotary Axis 2. Rotary Axis 2 uses an SG90 servo motor with a 0.7 degree step resolution. The length of the total arm for Rotary Axis 2, which includes Rotary Axis 3 as well, is 19.5 centimeters. We have a 0.08 and a 0.1 centimeter degree of error if the position point is at 12.53 and 14.94 and requires 71.43 steps. Here are the completed shear and moment graphs for the previous equations. These graphs reinforce the fact that our rotary axis will in fact stay reinforced given the amount of stress and weight that is put onto it. And last, we have a complete components list of rotary axis 2 given the pin, base, arm, motor, motor frame, and connection and their estimated weights. We have a total estimated weight of 0.3 kilograms with 5 parts. I will now be passing it to my colleague Peter, who will be discussing Rotary Axis 3.
Thank you, Brandon. I am Peter. I will be going over the Rotary Axis 3, which is the second linkage in the robot arm. So the main requirement of Rotary Axis 3 is that it provides rotary motion for the second linkage of the robot arm and holds the trigger actuator for the gripper and supports the gripper. RE3 is supported by Rotary Axis 2, and the mechanism for RE3 will be a servo motor attached to a pin so that whenever the servo motor is activated, the whole arm will turn. So here you can see the side view of the CAD for RE3. The top left is where the gripper attaches to, and the bottom right is one of the gears that is connected to the servo motor, but more on that in the next slide. So here you can see the exploded view of RE3. I've also included the exploded view of RE2 as well to help you better see how the servo is mounted. You can see the two mounting brackets coming off the back with the servo connected to the two gears. The component list is made up of the arm, which is made up of ABS plastic, servo motor, the mounting bracket, two gears, two screws to screw the servo in, and one pin, all adding up to about 0.18 kilograms. Here are the resolution calculations for RE3. The servo used for this has a 0.7 degree per step resolution, and the length of the arm is about 8.25 centimeters. If you look at the errors calculated below, this is for the farthest reaching point of the arm, and the errors are going to be so small because of how many steps the servo has to take. Here are the torque calculations for Rotary Axis 3. I've included a simple diagram and a table of inputs to show you how I got the mass moment of inertia torque. The torque from gravity was calculated from the point load from the gripper and the mass of the arm. The total torque was calculated to be about 0.0265 newton meters, which was expected from this arm because of the very low weight. Here's the Rotary Axis 3 motor selection. We needed a motor that supplied about 0.05 newton meters, but as you can see, this one provides about 0.245 newton meters. It allows for 180 degree rotation. Some things we were considering when picking this motor was lightweight and small, because we didn't want it to bang in anything while the arm was moving, and we didn't want it to affect the weight and torque that much. So as you can see from the servo motor specs table, it is indeed very lightweight and very small, so that meets our requirements. Here are the deflection calculations for RE3. The free body diagram to the right shows RE2 and RE3. You can see 2 point loads at the end of RE2 and another one at the end of RE3. You can see a uniform distributed load because material thickness and size is about the same for both of the arms. The calculated deflection was about 0.002 centimeters. Here are the shear and moment diagrams from the free body diagram of RE2 and RE3. As you can see in the shear diagram, the two drops are at the end of each of the arms, and from the moment diagram we get the max moment used for the stress calculations on the next slide. Here are the stress calculations for RE3. The two different tables solve for allowable bending stress and bending stress. The allowable bending stress was solved from the yield strength of ABS plastic and our safety factor of 2. As you can see, the bending stress is much lower than our allowable bending stress, so we do not expect failure for this RE3 arm. I will pass it on to Masden for the gripper assembly.
Thank you, Peter. My name is Masden Thomas, and now we're going to go over the gripper subsystem. And here you can see where the gripper subassembly is located and is at the end of Rotary Axis 3. Now to go over what the entire gripper subassembly is composed of, first we have the stabilization wrist servo, which is what powers the connection between the gripper and rotary axis 3. Next we have the magnetic crank and slider. This is the mechanism that is going to be used to actually release and pick up the steel ball bearings on the base plate. We have also the accelerometer, which is going to work in conjunction with the stabilization wrist servo, and this will keep the gripper subassembly normal to the base plate at all times. And lastly, we have the IR brake beam sensor, which is going to allow us to autonomously control the pick and place robot in order to pick up the steel ball bearings in specific locations. So here we have the CAD overview of the gripper subassembly. First off, we have the design we chose is an innovative cutout design which allows for a longer L2 sections and a wider range of motion for the actuator servo. We decided to choose the overall material for the gripper subassembly as ABS plastic, which allows us to have the unique shape that we chose, as well as tighter tolerances for all these screw placements and gear placements. For the crank and slider mechanism, we decided to use pins, stainless steel pins that will have set screws, which keeps them in place and everything components will be set. On the gripper here, you can see we have the actuator servo on the top, which is what uses power the crank and slider mechanism. We have the stabilization servo and the sensor assembly at the bottom, which is what we use to find the steel ball bearings on the base plate itself. To show more detail of the entire gripper subassembly, here we have an exploded view, which shows all the components and their respective parts. First off, we have the accelerometer, which is actually shown on the front of the faceplate of the gripper. We have the sensor assembly, which was mentioned before. And lastly, we have the crank and slider components that work inside of the gripper assembly. So to discuss the range of motion we have with the stabilization servo, in the figure 5.3, you can see we have a full range of motion of 180 degrees. This was obtained through the motor placement on the gripper itself, as well as using the MG92B servo that we selected as a stabilization servo. So in regards to the safety factor of these servos, considerations we had was small size and loading conditions, as well as motor torque failure of the servos. Factor safety what you chose for the servos was 3. And for the stabilization servo, we had a safety factor calculated of 6.1 and a safety factor of 4 calculated for the actuator servo. So now I'm going to hand it off to Alex, and he's going to go over some more of the calculations in regards to the gripper subassembly.
Thank you, Masden. My name is Alex South. As you can see here, our shear and moment diagrams for our gripper subassembly prove that the strength of the 3D printed ABS plastic that we will be using to create it is sufficiently strong under the loading conditions of the maximum loading, which would be perfectly horizontal in this case. You can see our maximum shear was calculated to be near 2 kilopascals, with our maximum moment at near 100 newtons per meter. Analyzing this further, we need to determine the maximum amount of deflection that this subassembly will be under during its maximum loading conditions. Using the formulas that you can see here, we found that our maximum deflection was near 3 to the -4 centimeters, which is sufficiently small for our applications. You can see here a breakdown of our different components with their various associated masses. Our total mass came in to 98 grams, including the payload during transportation. Using that calculated mass, we were able to calculate the required torque for the stabilization servo to turn our gripper subassembly. We used the formula for mass moment of inertia that you can see there at the top, and also the formula for torque, which you can see here on the side, which includes the acceleration of the gripper subassembly, as well as just the static forces and distances from the axis that those forces would be applied. We found that our total torque requirement was near 2.5 Newton centimeters, which is important for our decision on our correct servo to use for the stabilization. Using our torque requirements and our desired acceleration, we decided on the MG92B micro servo, which has an operating speed of 1.28 revolutions per second, and with its torque has a factor of safety of 6.1 at operating speeds, which is approximately half of the stall torque given in the specifications for the servo. And as you can see on the left, we determined that 1 radian per second squared was an optimal angular acceleration for our applications, and this was used to calculate the necessary torque. In addition to our stabilization servo, we had an additional servo to operate the crank and slider mechanism that detaches and attaches the magnetic tip to the payload. We call this the actuator servo. We had a few requirements when determining the lengths of this crank and slider mechanism, but the most important one is that the distance required to fully disconnect the magnet from the payload device, the payload steel sphere, was 0.9 centimeters. That came from the supplier. Using that value of 0.9 centimeters, we were able to determine that the length of L2 needed to be at least twice that in order to fully allow us to extend enough and retract enough to make sure that we were disconnecting and connecting from the magnet, or picking it up if we were slightly off with our other calculations. That gave us an action angle of 45 degrees to 135 degrees of when the servo would be under pressure or under torque while disconnecting from the magnet. That also gave us a housing distance, which is the distance from our motor to the center, essentially, of the magnetic tip of 5.715 centimeters. That allowed us to build it into CAD more effectively. And then using the previously mentioned equations up here, we were able to calculate L3 to be 5.05 centimeters for the optimal efficiency. The team then determined that we needed to calculate the perfect strength for our magnetic tip. If it were too strong, our actuator servo would be put under unnecessary strain, and too weak, we would lose the payload en route. Both of these situations are obviously unacceptable. We decided that the force of gravity on the payload was not the only force that would be applied to the payload, as the acceleration during the movement of the tip or gripper device would add an additional centripetal force to the payload that must be accounted for in the strength of the magnet. We found that this additional force and the force of gravity combined would be around 0.4 newtons, a required force from our magnet. Using a factor of safety of 3, we decided that our supplier force needed to be 2.24 newtons, which allowed us to pick a very small neodymium magnet or a slightly larger ceramic magnet as our optimal choice for our magnet.
So with the stroke calculations that Alex talked about earlier, here we have a side view of the crank and slider mechanism. Here you can see the exact dimensions of each linkage as well as the diameter of the pins. Now, the main source of failure that would occur in the crank and slider would be on these pins. So here we've calculated the shear stress, and the shear stress resulting from the force from the payload is 15.06 newtons per meter squared. So continuing with the crank and slider mechanism, here we show the exact torque calculations we acquired for the actuator servo and what would be required of the servo that we chose. So here we can find that the torque that is required given the force from the magnet is 0.08179 newtons per centimeter. So using the previous torque calculations from the last slide, we found that the sub-microserver SG51R fills its requirements and with a safety factor of 4. Another component involved in the gripper subassembly is the accelerometer. The accelerometer that we chose is the triple axis accelerometer breakout. What this does is it works in conjunction with the stabilization servo and will keep the entire gripper subassembly normal to the base plate at all times. The last component of the gripper subassembly is the sensor. So for this, we decided to use a 2168 photoelectric IR sensor. This utilizes an IR brake beam in order to find the location of the steel spheres. The sensors are comprised of a signal transmitter as well as a signal receiver. They operate accurately within 500 millimeters, and with the sensors only being 25 millimeters apart on the bottom of the gripper assembly, this ensures an accurate reading as well as a fast response time. Now, the reason that we chose this is a less expensive route, as well the sensors are already in line with the pickup placement for the gripper, meaning we only have to code one location in the final Arduino code. Now I'm going to hand this over to Alex and let him discuss the entire component list for the gripper subassembly.
Calculating out the price and mass of each of our components, we found that our total cost, not including labor, would be $72.15 or $72.15. That would be enough to cover all of our servos, all of our 3D printing for the gripper, and also all of the sensors and necessary components.
My name is Macri. I'm on the autonomous control subsystem of our pick-and-place robot assembly. On slide 79, you can see that this is a picture of our overall assembly. We have on the left arrow the instrumentation and control pointing towards where our MEGR board will be situated on the S2 subplate of our base plate. And you can also see in the right arrow our connection to the laptop where we'll upload our Arduino code so that the whole assembly can run autonomously. Slide 80 of our presentation deals with the autonomous control signals. It's essentially a logical progression of our pick-and-place autonomous code. It runs off of two functions. Function 1 deals with the S1 subplate where our position holes will be, where the balls will show up randomly. And Function 2 deals with the movement along the S3 subplate where our drop hole locations are, and also deals with the deployment and retraction of our gripper mechanism. It'll add position variables to both the drop hole and the position depending on whether there's a ball present or not. So on slide 81 we have our overall wiring diagram. This is all of the electrical components that are going to be playing a part in our autonomous code and wired into our Arduino MEGR board. On the left circle you can see we have the manual controller components. It is two thumb joysticks, one that will actuate RA1 and the other one will actuate RA2 and RA3 in sync so that we can move the entire arm with just two thumb joysticks. We then have three buttons that deal with the gripper actuation for the crank slider mechanisms for picking up and dropping off the balls, and we also have one that will be power. And then we also at the top circle have the stepper motor, driver, and micro switch. The stepper motor and driver will operate RA1, and the micro switch will be used to home that stepper motor so that it does not lose track of its position. We then have four servos, one for RA2 to actuate the linkage, and another servo for RA3 for actuation. We also have a servo for gripper stabilization to keep our gripper mechanism normal to the base plate for smooth pickup and drop off of balls. And then we also have an actuation servo for the gripper, which will be the one that moves our crank slider mechanism within the gripper to actually pick up the balls with our magnet. And in the bottom circle we have our infrared emitter and receiver, which are the sensors that are located on the bottom of the gripper. And everything will be wired to a common power source and ground that goes to our Arduino MEGR. And another consideration that was made was the lengths of our wires, because if our arm overextends our length of our wires, we might pull a plug and the whole thing will stop working. So the maximum length of our arm is 19.76 centimeters. We're never going to achieve that length. That was if it was fully extended, but just for a factor of safety, we wanted to consider that that was the maximum distance that our arm will ever extend. So all of our wires are over 20 centimeters long, or actually they are exactly 20 centimeters long. So we'll never really come close to pulling a plug and turning off our robot on accident.
Hello, my name is Jonathan Pauli, and I am in charge of the manual controls for the PAP robot. As you can see, we have two 2-axis joysticks, one that controls rotary axis 1, and the other one controls rotary axis 2 and 3. We have three push buttons, one that overrides the autonomous control, and the second one engages the gripper system, and the third disengages the gripper system. As you can see here, this is the controller dimensions from the top view. The width comes in around 150 millimeters, which is approximately a little bit under 6 inches, and the depth is 80 millimeters, and the height is around 60 millimeters. The controls component list includes the MEGR, obviously, the jumper wires, the stepper motor, the motors for the rotary axis 2 and 3, and the stabilization motors, and as well as the actuation motors, the joysticks, and the buttons. This is the PAP assembly mass breakdown. As you can see, the base plate takes up the majority of the weight, and the total mass comes up just below 3 kilograms. So it's 2.99 kilograms. And I will hand it over to Peter.
This is the uncertainty analysis for Team 5's Pick and Place Robot. The 4 holes that we are reporting are the worst uncertainties that we've calculated, and the holes are 1, 6, 19, and 21, as you can see on the diagram to the left. The first table is the inputs for calculating theta positions and such for the inputs for the sensitivity equations. And the second table is the worst 4 hole uncertainties in the x and y directions.
Alright, so on this slide you can see the homing sequence of rotary axis 1. So essentially, sequence number 1, the rotary axis 1 is going to contact the micro switch, and at that point we do know the position of rotary axis 1, and from there we can step the stepper motor of rotary axis 1 accordingly to move to any position that we choose to move to. Here's a summary of the rapid prototyping components. Here we have the gripper housing, the gripper gears, gripper crank and slider components, the manual controller housing, RA2 linkage, and RA3 linkage. Here we have the manufacturability of each subsystem. And this is a lot to go over here, but there are only a handful of actual manufactured parts. You can see the base plate has the actual material, which is the Garolite G10 FR4 sheets that are manufactured, as well as the aluminum rods for the standoffs. And for RA1, the 6061 aluminum sheet that would be used for the bracket that will also be manufactured, as well as the shaft that connects RA1 to RA2. And for RA2, we have the pin that is manufactured, as well as the base and the arm. For RA3, we have the arm, which is manufactured, and also the pin. And for the gripper, we have the housing and gears, which is, rapid prototyping. For the autonomous controls, there is nothing that will actually have to be manufactured. Everything will be purchased. And for the manual controls, the only manufactured part is the actual housing. So here we have our labor budget, and assuming $10 per hour for student labor, we come out with a total of $285 for our labor budget. So for the components, labor, and manufacturing, we have a total of $580 combined. And for the rapid prototyping, we have a total of $140 for a grand total of $720 for the entire assembly. And once again, here is an overview of our entire pick and place robot assembly. So in summary, the purpose of this pick and place robot is to pick up and drop off 4 steel spheres with 3 rotary axes and a gripper attached to a base plate. And this pick and place robot will be controlled using both autonomous and manual controls. And the pick and place robot that we as Team 5 have designed has a total mass of 2.99 kilograms and a total cost of $720. If you have any questions regarding our pick and place robot, we would love to hear from you now.